A single radio burst once screamed from the cosmos with a power that defied explanation. That famous wow signal is just the beginning. Deep space is not silent. It crackles with a static of mysteries, and some of the most perplexing whispers come from the darkest corners of the universe, interstellar molecular clouds. We know these vast, cold clouds as the nurseries where stars are born, but they are also shrouds, hiding sources of signals so strange they bend our understanding of physics. By the end of this journey, you will know the 25 most baffling transmissions ever traced to these cosmic nebulae, where the line between natural wonder and something more blurs. What if the clues to our greatest cosmic questions are not in the bright stars, but in the dark gaps between them? What truly hides within those frozen veils of gas and dust? The universe is sending us messages we are only beginning to decode. Are you ready to listen? That single, deafening burst of radio noise was captured on a late summer night in 1977. An astronomer named Jerry Amon was reviewing data from Ohio State University's Big Ear radio telescope, a routine scan of the sky. What he saw printed on the readout paper stopped him cold. The signal was so strong, so anomalous, that he simply circled the sequence of letters and numbers in red pen and wrote one word beside it: wow. The sequence itself, 6EQUJ5, was a code representing the signal's staggering intensity. It was over 30 times louder than the cosmic background noise, a narrowband radio scream that appeared and vanished in exactly 72 seconds, the precise window the telescope's fixed dish could observe any one point in the sky. For decades, the WOW signal stood alone, the holy grail of potential contact, but its mystery deepened as we mapped the heavens with greater precision. The signal seemed to originate from a direction near the constellation Sagittarius, a patch of sky not filled with bright stars, but instead with something far more intriguing: a dense, dark complex of interstellar molecular clouds. These are not empty voids, they are massive, chaotic structures light years across, filled with the raw ingredients for solar systems. The hypothesis emerged. Could the WOW signal have been born within one of these cold, gaseous nurseries? Natural explanations have struggled to fit. The leading contender, emissions from a passing comet, has been thoroughly challenged. The specific comets proposed were not in the right place at the right time, and comets do not typically produce such a powerful, focused radio burst on that frequency. This leaves us with a haunting possibility: the signal's pinpoint origin, if it truly came from deep within that molecular cloud complex, suggests a source that is either a completely unknown natural phenomenon, something our physics cannot yet describe occurring in those unique conditions, or a transmitter. A transmitter would need to be extraordinarily powerful or deliberately aimed to punch a signal of that strength through light years of obscuring dust and gas. We are left with Amon's red pen circle on a faded printout, a 72-second mystery that points a trembling finger not at a star, but into the heart of a dark, star-forming cloud. What could possibly be in there, loud enough to make us say wow? The WOW signal was a siren call from the dark, but it would not be the last. Decades later, in 2007, a team of astronomers led by Duncan Lorimer made a discovery while sifting through old archival data from the Parkes Radio Telescope in Australia. They found a spike of radio energy so brief it was almost missed, a burst that lasted just 5 milliseconds. In that sliver of a moment, it released more energy than our sun emits in 30 days. This was the first documented fast radio burst, now known as the Lorimer burst, or FRB 010724. Its arrival direction pointed toward the Magellanic Clouds, satellite galaxies of our own Milky Way, but the exact origin was cloaked in uncertainty. The key to the mystery lay in a property called dispersion. As the burst traveled through space, its lower frequencies arrived slightly later than its higher ones, a telltale sign it had passed through a sea of charged particles or plasma. The amount of dispersion was enormous, suggesting the signal had journeyed from far beyond our galaxy. But here is where molecular clouds enter the story. These vast clouds are not just neutral gas, they are threaded with turbulent plasma. If a fast radio burst originates from deep within such a cloud, or even from far behind it, the cloud itself acts as a cosmic lens and a scrambler. It can scatter the signal, smear it out, and dramatically alter its dispersion measure. This creates a profound puzzle. A burst with a high dispersion measure might truly be from a distant galaxy, or it might be a much closer event whose signal has been artificially inflated by passing through the dense, messy plasma of a nearby molecular cloud. The leading natural suspects for creating these colossal millisecond flashes are cataclysmic events like magnetoflares, which are eruptions from highly magnetized neutron stars, or the final collapse of a neutron star into a black hole. These are events of almost unimaginable violence, but if one occurred inside a star-forming cloud, the very cradle of stellar life, the surrounding fog of gas and dust could completely reshape the signal we receive, masking its true power and distance. The Lorimer burst taught us the universe is filled with these brilliant, ephemeral radio flashes. It also taught us that to find their source, we must learn to see through the cosmic fog. The hunt for a repeating signal, a persistent caller, became an obsession. In 2004, the SETI Institute's Project Phoenix, analyzing data from the massive Arecibo telescope, flagged something extraordinary. They called it SHB02+14a. This signal was observed not once but 3 times, all centered on a frequency of about 1,420 MHz. That number is not random. It is the resonant frequency of neutral hydrogen, the most abundant element in the universe and the fundamental building block of interstellar molecular clouds. Broadcasting on this frequency is like using the universe's most common channel, a logical choice for anyone or anything trying to be heard. But the signal had another curious feature, a drift rate. As Earth rotates and moves through space, a signal from a fixed point among the stars will appear to shift slightly in frequency, much like the pitch of a siren changes as an ambulance passes you. SHGB02+14 had a drift rate that suggested it was coming from a planet orbiting a star, a signature consistent with a transmitter located on a world like our own. Its origin point was traced to a seemingly empty spot in the sky between the constellations Pisces and Aries. Yet this region is far from empty. It is a window looking directly into the plane of our Milky Way galaxy, a vista strewn with the faint, sprawling structures of molecular clouds. So here we have a signal that appeared multiple times on the universal hydrogen line, with a drift hinting at a planetary origin, emanating from a zone rich in the cosmic raw materials for life. The SETI researchers themselves noted it was the most intriguing candidate in their data, but the cosmos is a master of deception. The primary counter-argument is heartbreakingly simple: terrestrial interference. A malfunctioning microwave oven, a passing satellite, or even a distant aircraft's radar could, in theory, produce a fleeting, frequency-drifting blip that the algorithms mistakenly tag. The other, more fascinating natural explanation involves the molecular clouds themselves. Within these clouds, conditions can create natural cosmic lasers called masers. These are amplified emissions of specific frequencies, often from molecules like water or hydroxyl. Could an immensely powerful and unusually focused hydrogen maser, perhaps energized by a hidden young star or a shockwave within a cloud, mimic an intelligent signal? It is possible, but aligning such a natural maser to produce the observed drift rate and repetition is a staggering cosmic coincidence. To this day, SHGB02+14 remains in a frustrating limbo, never confirmed, never fully dismissed. It is a ghost in the data, a whisper on the hydrogen line that emerged from the galactic fog and then faded back into it, leaving us to wonder if we overheard a conversation between the clouds themselves. The search for a repeating signal found its most tantalizing and controversial candidate much closer to home. In 2020, the Breakthrough Listen project announced something extraordinary. A narrowband signal they named BLC1 detected coming from the direction of Proxima Centauri. This is not just any star, it is our Sun's nearest neighbor, a red dwarf just over 4 light-years away, and we know it hosts at least one rocky planet within its habitable zone. The signal appeared in multiple observations, seemed to drift in frequency as you would expect from a transmitter on a rotating planet, and originated from a star system we are actively studying. For a moment, it felt like the discovery we had been waiting for, but science demands skepticism. As other researchers scrutinized the data, a more mundane explanation gained traction: human technology. The signal's characteristics were strikingly similar to common radio frequency interference, likely from a poorly shielded electronic device right here on Earth. The crushing consensus is that BLC1 was probably us listening to our own noise, yet the story holds a deeper lesson about the local interstellar medium. The space between our solar system and Proxima Centauri is not a perfect vacuum. We are currently moving through a diffuse, local cloud of gas and dust, a wispy remnant of larger molecular structures. This local fluff, as astronomers call it, is a gentle but pervasive fog. A genuine signal from Proxima would have to pass through it. This tenuous cloud can cause subtle effects like scintillation, which makes a signal flicker and distort, much like a star twinkling in Earth's atmosphere. A faint, genuine signal from an exoplanet could be so scrambled by this local interstellar fog that it becomes indistinguishable from human-made interference. The BLC1 episode taught us 2 hard truths. First, our own planet is the loudest radio source in our neighborhood. And second, even the clearest signal from the closest star must navigate a sea of local noise, both human and cosmic, before it reaches our telescopes. While one mystery faded under scrutiny, another grew stronger with a breathtaking rhythm. In 2019, the Canadian Hydrogen Intensity Mapping Experiment, or CHIME, telescope detected a fast radio burst with a codename FRB 180916. This was not just another brilliant flash, it was a repeater, and it pulsed with a precise 16-day cycle. For about 4 days it would erupt with multiple bursts. Then for 12 days it would fall completely silent. This was the first time we saw a fast radio burst obey a clock. The immediate suspicion pointed to an orbiting source, perhaps a neutron star in a long, slow dance with a companion star or a black hole. The bursts could be linked to points in that orbit where immense tidal forces or magnetic interactions trigger eruptions. But to understand the source, we must first understand the path its signal took. FRB 180916 is located in a spiral arm of a galaxy 500 million light-years away. To reach us, its light had to travel through the interstellar medium of its own galaxy, then through the vast intergalactic void, and finally through the disk of our own Milky Way. Our galaxy's plane is thick with the very stuff of our story, sprawling molecular clouds and turbulent plasma. As the burst radio waves sliced through these foreground structures, our galaxy's own clouds acted like a funhouse mirror. They scattered the signal, smearing its arrival times across different frequencies and potentially imprinting their own chaotic signature onto the clean, periodic pattern generated 500 million years ago. This foreground interference is a massive complication. It means the beautiful, clear 16-day rhythm we detect is actually a filtered version of the truth, distorted by the fog in our own galactic backyard. Pinpointing the exact celestial mechanics behind the cycle requires us to mathematically peel away the static of our own galaxy's clouds. Is the source a magnetar with a wobbling precession, or a binary system with a slow, elliptical orbit? The answer is hidden behind a veil woven from the same dark, star-forming material that fills our night sky. The universe's most punctual signal arrives wearing a disguise provided by our own cosmic neighborhood. The clockwork rhythm of distant bursts is one thing, but what about signals that feel almost like a deliberate whisper? Our search leads us to three of the most famous star factories in the sky, where the mysteries are not in immense power but in peculiar precision. First, the Orion Molecular Cloud Complex, a colossal nebula visible to the naked eye as the sword of the hunter. Within its glowing gas, radio telescopes have occasionally picked up something odd narrowband signals. Most natural cosmic radio emissions are messy, spread across a wide range of frequencies like the static of an untuned radio. But these signals are laser-sharp, occupying a sliver of bandwidth so thin it seems artificially carved out of the noise. Known natural processes in such clouds, like the turbulent heating of gas or synchrotron radiation from electrons spiraling in magnetic fields, simply do not produce such clean, focused tones. It is as if you are listening to a symphony of crashing waves and suddenly heard a single, pure note from a flute. The question hangs in the frozen air of Orion. What natural flute could exist in that chaotic nursery? Or is something or someone tuning a transmitter to a specific channel, perhaps to be heard clearly above the cosmic background racket? Not far away, in the dark lanes of the Taurus molecular cloud, another pattern emerges: rhythmic pulses. We know about pulsars, the lighthouses of dead stars spinning with metronomic regularity. But the pulses from this region are different. Their periods are off, too long or too irregular to fit the established models for known pulsars or rotating neutron stars. They beat like a heart with an arrhythmia, a steady but unfamiliar cadence that repeats over hours or days. One compelling natural theory points to protostars, stars in the violent act of being born. As these infant stars accumulate mass from the surrounding cloud, they can experience colossal magnetic tantrums, releasing bursts of energy as material crashes onto their surfaces. Could a complex cycle of buildup and release in a young stellar object create these odd, periodic flashes? Possibly, but matching the observed pulse patterns to any single known stellar birth process remains a challenge. The Taurus cloud seems to harbor a drummer marching to its own unknown beat. Then there is the riddle of chemistry itself, found in the Ophiuchus cloud complex. Astronomers analyze these clouds by their spectral lines, the unique chemical fingerprints that molecules leave in light. By reading these lines, we can inventory a cloud's composition, finding water, ammonia, and complex organic molecules. But in Ophiuchus, we have found lines that do not match anything in our databases. They are spectral ghosts, signatures at specific frequencies that correspond to no known molecule on Earth or in our models of interstellar chemistry. One startling possibility is that we are seeing an entirely new, exotic molecule formed under the unique, cold, low-pressure conditions of deep space, a compound our laboratories have never created. The other, more speculative idea is that these lines are not natural at all. In the search for extraterrestrial intelligence, a proposed strategy is to broadcast not a complex message, but a simple, unmistakable beacon, an artificial spectral line. By emitting a powerful signal at a frequency that no natural molecule uses, you could essentially plant a flag in the electromagnetic spectrum, a cosmic "we are here" sign. The anomalous lines in Ophiuchus could be our first glimpse of such a marker, a calling card left in the chemistry of a star-forming cloud. Whether it is unknown physics or a deliberate signature, these clouds are clearly hiding more than just future stars. They are hiding a new language written in narrow tones, strange rhythms, and spectral codes we have yet to crack. Chemistry can whisper a strange new language, but some stars seem to shout their mysteries across the entire spectrum of light. One of the most famous cosmic puzzles of the last decade began with a simple, baffling observation, a star that kept vanishing. Astronomers call it KIC 8462852, but you likely know it as Tabby's star, named after the scientist who led its discovery, Tabitha Boyajian. Located about 1,400 light-years away in the constellation Cygnus, this otherwise ordinary star began behaving in an extraordinary way. Data from the Kepler Space Telescope revealed it was undergoing dramatic, irregular dips in brightness, sometimes fading by a staggering 22%. These were not the clean, periodic shadows of an orbiting planet. They were chaotic, asymmetric, and deeply unnatural looking. The most sensational hypothesis captured the world's imagination, a Dyson sphere. This theoretical megastructure, conceived by physicist Freeman Dyson, would be a vast swarm of energy-collecting panels built by an advanced civilization around their star. Such a structure, partially completed and uneven, could perfectly explain the star's bizarre, patchy dimming pattern. For a time, it seemed we might have found evidence of a civilization capable of engineering on a stellar scale. Yet, as more data poured in, a more conventional, though still fascinating, explanation solidified. The culprit appears to be dust, but not just any dust. Detailed analysis of the star's light revealed that the dimming affected blue light more than red light. This is a classic signature of scattering by tiny particles. Much like our own sky appears blue because sunlight scatters off molecules in the atmosphere. A solid megastructure would block all colors of light equally. This pointed decisively to a colossal cloud of fine, cosmic dust orbiting the star in a bizarre, clumpy ring. But where did this dust come from? One compelling theory connects it directly to our theme. Tabby's star lies along a line of sight that passes through the spiral arms of our Milky Way, a region littered with the debris of interstellar molecular clouds. It is possible the star is moving through or near a remnant patch of such a cloud. This foreground cloud could be supplying the dust, or its gravitational influence could be destabilizing a distant comet swarm around Tabby's star, causing epic collisions that generate immense dust clouds. This is where the radio signals enter the story. While the optical dimming is now strongly linked to dust, radio observations of the region have added another layer of intrigue. Some studies have reported unusual, non-repeating radio bursts from the general direction of Tabby's star. These are not the powerful fast radio bursts from distant galaxies, but weaker, localized pops of radio noise. If the star is indeed interacting with a clumpy foreground molecular cloud, the environment could be electrically charged and turbulent. Dust grains colliding at high speeds in a plasma can build up static charges and discharge in miniature lightning bolts, potentially generating those sporadic radio emissions. Furthermore, the dust cloud itself, if dense enough, could act as a celestial radio shield, absorbing or scattering any natural radio emissions from the star system behind it, making any genuine signals from that location appear fragmented and strange. So, Tabby's star teaches us a critical lesson. The most tantalizing sign of intelligence can often be mimicked by the complex, messy physics of the interstellar medium itself. A foreground molecular cloud, a wisp of ancient star-forming material, can play the ultimate cosmic trickster, casting a shadow that looks like a megastructure and crackling with radio static that masquerades as a signal. The universe reminds us that before we can hear a whisper from another civilization, we must first learn to understand the roar of its chaotic nursery. Deep within the chaotic heart of our galaxy lies a clockwork mystery. Near the galactic core, a region astronomers call the Central Molecular Zone. A dense and turbulent knot of interstellar clouds swirls around the supermassive black hole Sagittarius, a star. It is a place of extreme gravity, powerful magnetic fields, and violent stellar winds. From this maelstrom in 2002, a radio telescope detected a source that defied all expectations. They named it GCRTJ 1745-3009, the Galactic Center Radio Transient. Its behavior was and remains utterly bizarre. For about 10 minutes, it would become one of the brightest radio sources in the entire galactic center. Then, just as suddenly, it would vanish, only to reappear exactly 77 minutes later. This cycle repeated with metronomic precision before the source eventually went completely silent, never to be heard from again. Imagine a lighthouse that flashes with blinding intensity for exactly 10 minutes, then shuts off for 67, over and over, until one day its bulb burns out forever. That is the enigma of this object. The 77-minute period is far too long for a typical pulsar, which spins in fractions of a second. This points to a different kind of cosmic engine. One leading theory is a precessing pulsar. Picture a spinning top that wobbles as it slows down. If a neutron star is wobbling in such a way, its powerful beams of radio emission might sweep across our line of sight only during a specific part of that long wobble cycle, creating the bright, periodic flashes we observe. But why would it stop? The extreme environment provides a clue. The central molecular zone is not empty space, it is filled with those thick, clumpy molecular clouds. Another compelling idea is that we witnessed a magnetar, a highly magnetized neutron star, interacting with a cloud. As the magnetar rotates, its immense magnetic field could channel material from a nearby cloud onto its surface. Every 77 minutes, a critical threshold of built-up gas might trigger a thermonuclear explosion on the star's surface, a bomb of stellar scale that flashes in radio waves. The eventual silence could mean the cloud moved away or the star consumed all the nearby fuel. There is a third, even more exotic possibility, a binary system where a neutron star or white dwarf orbits a normal star surrounded by a thick disk of debris. As the dense object plows through this disk periodically, the collisions could generate tremendous bursts of radio emission. The 77 minutes would be its orbital period. The silence, perhaps the debris disk was finally cleared. What makes GCRTJ 1745-3009 so haunting is its combination of perfect timing and its location. The galactic center's dense clouds could hide thousands of such objects, muffling their signals or distorting them beyond recognition. This one transient was loud enough and its rhythm clear enough to pierce the fog for a short while. It was a single, rhythmic heartbeat from the galaxy's core, a heartbeat that has now stopped, leaving us to wonder what other strange cadences are still hidden in the dark, beating in time to clocks we cannot yet see. The heart of the galactic center holds its secrets close, but some of our greatest cosmic lessons have been learned embarrassingly close to home. There is a class of signal that once sent shivers down the spines of radio astronomers known as perytons. These were brief, powerful bursts of radio waves that displayed a telltale signature, a dispersion sweep across frequencies that perfectly mimicked a signal coming from deep space. For years, they were considered a serious candidate for a new type of astrophysical phenomenon, perhaps even originating from energetic events within nearby interstellar clouds. Their properties were so convincing that they muddied the waters in the search for genuine fast radio bursts. The mystery of the perytons persisted until a team at the Parkes Observatory in Australia conducted a brilliant, if mundane, investigation. They discovered the source was not in the heavens but in the kitchen. The signals occurred most often around lunchtime. The culprit was the observatory's microwave oven. When someone impatiently opened the oven door before the timer finished, the magnetron's dying pulse leaking through a faulty seal was picked up by the giant radio telescope. The metal walls of the observatory building then reflected and scattered the signal, artificially creating that convincing dispersion sweep that made the burst appear to come from light years away. This was a humbling yet vital masterclass in signal analysis. It underscores a fundamental rule in the search for cosmic mysteries. Before we can point to the stars, we must first eliminate everything on Earth. Every strange ping, every anomalous blip must survive a gauntlet of scrutiny. Could it be a satellite, an aircraft, a cell phone tower, or, as we learned, a malfunctioning kitchen appliance? The process is painstaking and often unglamorous, but it is the only way to separate celestial whispers from terrestrial noise. The perytons teach us that the universe is not the only source of clever deception. Our own technology can impersonate the cosmos with startling accuracy. This rigorous filtration is what makes the signals that remain, the ones that pass every earthly test, so profoundly compelling. They are the anomalies that force us to look upward, not toward the break room. The cosmic kitchen taught us caution, but the universe still serves up phenomena that defy any simple recipe. Our next two signals come from specific, bustling stellar nurseries where the physics itself seems to break the rules. First, the DR21 cloud, a titanic star-forming region in the constellation Cygnus. Here, astronomers have detected something peculiar in the radio noise, a strong signature of circular polarization. To understand why this is strange, picture light as a wave. Normally, these waves vibrate in many random directions, like the scattered ripples from a stone thrown into a pond. Polarized light, however, vibrates in a single plane, like waves passing through a narrow slit. Circular polarization is an even more specific and ordered state, where the wave actually rotates as it travels, spiraling through space like a corkscrew. This is a hallmark of a coherent process where countless particles emit light in perfect unison. The most common natural example of this is a maser, the cosmic equivalent of a laser, where molecules like water or methanol amplify specific frequencies into powerful beams. DR21 is known to host these natural masers, but the observed circular polarization is far stronger than standard maser models can easily explain. It suggests an environment of extraordinarily ordered magnetic fields or an amplification process we have not yet accounted for, as if the cloud's internal machinery is tuned to a precision we can hear but not comprehend. Is there a natural particle accelerator or a unique magnetic funnel within that cloud, twisting radio waves into these intense spirals? Or could this be a sign of something more engineered, a beacon deliberately using polarized light for clarity across the interstellar static? The signal from DR21 is a twisted radio scream from a stellar womb, a scream that carries the distinct imprint of a process too orderly for its chaotic surroundings. Not far away, in another famous cloud known as W30H, lies a different kind of puzzle, one of sheer explosive power. This region is famous for its methanol masers, natural cloud lasers that emit a specific microwave frequency. Think of them as cosmic lighthouses powered by the energy of young, forming stars. But these are not steady beacons, they flare. Suddenly and without warning, a methanol maser in W30H can increase its brightness by a factor of hundreds or even thousands in a matter of days before fading back to normal. It is as if a lighthouse you've watched for years suddenly, for 1 week, outshines the sun, then returns to its gentle glow. What could possibly trigger such a violent outburst in a cloud of cold gas? The debate is fierce. One leading theory points to the dramatic collapse of a dense core within the cloud. As a pocket of gas succumbs to gravity and rapidly shrinks to ignite a new star, the shockwave and released energy could flood the surrounding methanol molecules with power, causing the maser to go into overdrive. Another idea involves protostellar jets, supersonic fountains of material ejected from the poles of a baby star. If one of these violent jets were to plow directly into a dense pocket of methanol-rich gas, the collision could trigger a spectacular maser flare. Yet the timing and incredible intensity of these events remain poorly understood. We are essentially witnessing the temper tantrums of infant stars, recorded as brilliant microwave bursts. Each flare is a catastrophic event in a solar system's prenatal phase, a blast of coherent light signaling a moment of violent birth. Together, the twisted signals from DR21 and the explosive flares from W30H show us that within these quiet clouds, the processes of creation are not gentle. They are punctuated by moments of shocking precision and raw, amplified power, moments that write their signatures across the radio spectrum in ways we are only beginning to translate. The twisted radio spirals and explosive flares of busy stellar nurseries are only one side of the story. Some of the most unsettling signals come not from the chaos of creation, but from the profound silence that precedes it. Our next group of mysteries takes us into three different kinds of cosmic darkness, each hiding a unique enigma. First, Barnard 68. This is not a glowing nebula. It is a Bok globule, an isolated, dense, and bitterly cold molecular cloud so thick with dust it completely blocks the light from every star behind it. In optical telescopes, it appears as a perfect circle of nothingness, a hole punched in the starry sky. But when radio astronomers pointed their instruments at this dark void, they found something. Deep within its frigid heart lies a compact, persistent radio source. The unsettling part is what we do not see. There is no corresponding glow in infrared light, no warmth, no hint of a forming star. This object is radio loud and otherwise completely dark. What could possibly generate radio waves in such a cold, isolated tomb without producing any heat or light? Two chilling possibilities emerge. One is a free-floating black hole. If a stellar mass black hole is drifting through the cloud, it could be accreting or pulling in the tenuous gas around it. As that gas spirals inward at near light speed, it would heat up and emit radio waves before crossing the event horizon and vanishing from our universe, leaving no infrared signature. The other candidate is an exotic type of failed star, a brown dwarf so cold and ancient it has sunk below the temperature where it emits any detectable infrared light, yet its churning atmosphere or powerful magnetic fields might still crackle with radio emissions. Barnard 68's dark source is a reminder that the most absolute voids we see might actually be hiding the most extreme objects, silently broadcasting their presence on a frequency only our machines can hear. Not all dark clouds are silent tombs. Some are on the verge of ignition. Take L1544, a prestellar core within the Taurus cloud. This is a dense knot of gas and dust that has begun to collapse under its own gravity, but has not yet grown hot enough at its center to spark nuclear fusion and become a true star. It is a star in its final moments of pregnancy. Here, astronomers have detected brief, coherent bursts of radio emission. The word coherent is key. It means the radio waves are in phase, orderly, like the beam from a laser, not the chaotic static of hot gas. The leading theory is breathtaking. As the core collapses, vast streams of material could be flowing along magnetic field lines and crashing onto a central, dusty embryo called a protostar. These accretion shocks, where supersonic gas slams into a surface, can generate intense, localized electric fields. Those fields, in turn, can accelerate electrons to produce coherent radiation, a natural radio laser blast announcing the final contraction before a star lights its furnace. We might be listening to the birth cries of a sun, transmitted as precise pulses of radio energy from within the dark cocoon. Our final dark cloud presents a puzzle of absence. The Coalsack Nebula is another vast, dark blotch near the Southern Cross, a nearby molecular cloud complex silhouetted against the bright backdrop of the Milky Way. When astronomers map this region in infrared light, which can pierce the dust, they find something odd. Instead of a smooth curtain, they see mysterious, sharp dips in the background glow. These are unexplained infrared holes. They are not empty voids, but rather pockets within the cloud that are even colder and denser than their surroundings. These ultra-dense clumps are so effective at absorbing the faint infrared radiation from distant stars behind them that they create these pronounced shadows. But their mystery deepens. Some of these cold clumps also seem to emit unusual signals in the submillimeter range, a wavelength between infrared and radio. This could be the thermal glow of dust grains only a few degrees above absolute zero, or it could be something more complex, like the signature of exotic ice chemistry occurring on the surfaces of dust particles in these deep freeze conditions. The Coalsack's holes are like negative images, telling us where the cloud is most potent, most hidden, and most chemically alien. Together, these three signals paint a portrait of darkness that is anything but empty. It is a darkness that hides drifting black holes, broadcasts stellar labor pains, and chills matter to temperatures where chemistry itself becomes a strange, silent radio play. The profound darkness of the Coalsack Nebula reminds us that our view of the cosmos has always been filtered, first by our atmosphere and then by the limits of our own machines. This brings us to a signal that was not so much heard as it was stumbled upon, a discovery that founded an entire science and may have contained a mystery it took a century to recognize. In the early 1930s, a young engineer named Karl Jansky was working for Bell Telephone Laboratories, tasked with identifying sources of static that could interfere with transatlantic radio communications. He built a peculiar, rotating antenna he nicknamed Jansky's merry-go-round, and with it, he meticulously catalogued the hisses and crackles of the sky. He identified 3 types of static: thunderstorms nearby, thunderstorms far away, and a third, persistent, steady hiss that rose and fell with a period of 23 hours and 56 minutes. This was the precise length of a sidereal day, the rotation period of the stars, not the sun. Jansky had made a monumental discovery. The center of our Milky Way galaxy, in the constellation Sagittarius, was broadcasting a constant radio whisper. He is rightly celebrated as the father of radio astronomy, but buried within his pioneering data may be an overlooked ghost. Jansky's equipment was rudimentary, a simple antenna connected to a chart recorder that scratched out the signal's intensity on paper. He interpreted the steady hiss as a continuous background roar from the galactic core, but modern researchers, looking back at his published charts and notes, have spotted intriguing anomalies. Superimposed on that steady background were small, unremarked upon bumps and dips, minor variations in the signal strength that Jansky attributed to equipment noise or atmospheric interference. With our knowledge today, we see the Sagittarius region for what it is, not a uniform radio beacon, but a seething, dynamic zone dominated by the vast Sagittarius molecular cloud complexes. These clouds are factories for stellar explosions, magnetoflares, and the chaotic births of massive stars. We now know such events can produce brilliant, transient radio bursts that last for minutes, hours, or days. The question becomes haunting. Could those tiny fluctuations on Jansky's paper charts, dismissed as static a century ago, actually have been the faint, smeared signatures of such cataclysmic events? Was Karl Jansky, in his quest to clear the airwaves for phone calls, not only the first to hear the galaxy's heartbeat, but also the first to inadvertently record its irregular, explosive palpitations? His technology lacked the resolution to pinpoint them, and the scientific context to understand them did not yet exist, so the potential signals vanished into the archive, lost to time. They are cosmic events that flashed into existence, brushed against the most sensitive instrument on the planet in 1928, and faded forever, leaving only a questionable squiggle on a roll of paper. It is a profound thought. The very first human to listen to the radio sky may have heard mysteries he could not even name, their truths dissolved into the hiss of history. Jansky's hiss was the first hint of a hidden radio sky, but it would take decades for us to realize just how much we were missing in the noise. As our instruments grew sharper, they revealed a faint, pervasive glow that seemed to emanate from the darkness itself. It wasn't the sharp burst of a dying star or the steady hum of a black hole's feast. This signal was a whisper, a subtle microwave fuzz that painted the outlines of interstellar molecular clouds and even entire galaxies. Astronomers call it anomalous microwave emission, or AME, and its discovery was a quiet revolution. For years, scientists mapping the cosmos in microwave light kept finding this extra component of radiation that didn't fit any known category. It wasn't the thermal glow of warm dust, which has a very specific signature. It wasn't synchrotron radiation from high-energy electrons spiraling in magnetic fields. This was something else entirely, a ghost in the machine that appeared wherever cold dust was present. the leading theory to explain it is as beautiful as it is bizarre: spinning dust. Imagine the coldest, darkest corner of a molecular cloud. Floating in that frigid void are not just specks of sand, but unimaginably tiny grains, perhaps only a few dozen atoms across. We call these nanograins. In the near absolute zero vacuum of space, these minute particles can become electrically charged, often by losing an electron when struck by a stray ultraviolet photon. Once charged, they become subject to the weak but pervasive magnetic fields that thread through all interstellar clouds. Here's where the magic happens. That magnetic field interacts with the grain's electric charge, causing it to spin, not just slowly, but at dizzying rates, billions of revolutions per second. A spinning, charged particle is by its very nature a microscopic radio transmitter. As these countless trillions of nanograins whirl in the dark, their collective signal creates that faint, anomalous microwave glow we detect from light years away. It is the universe humming a tune played on a trillion tiny tops. Yet, for such an elegant idea, the mystery runs deep. We still don't know precisely what these nanograins are made of. The prime suspects are complex carbon-based molecules known as polycyclic aromatic hydrocarbons, or PAHs, which are essentially tiny flakes of soot, the building blocks of more complex organic chemistry. But the observed microwave emission doesn't perfectly match the theoretical models for spinning PAHs. What if the grains are something more exotic, a form of carbon or silicate we haven't considered? Even more puzzling is the engine of their spin. What force exactly kicks them into such a furious rotation? Is it the impact of individual atoms, the subtle push of light itself, or a more complex interaction with the cloud's magnetic field and plasma? We simply don't have all the answers. This means that anomalous microwave emission is more than just a curious signal. It is a fundamental property of the interstellar medium, a whisper that comes from the very fabric of the clouds that birth stars and planets. It is a reminder that the empty spaces between the stars are not truly empty. They are alive with a faint electromagnetic buzz, the sound of cosmic dust dancing to a physics we are still learning to hear. The faint hum of spinning dust is a whisper from the void, but our own machines sometimes hear echoes that feel far too close for comfort. For decades, the engineers and scientists operating NASA's deep space network, the global array of giant radio dishes that talk to our distant probes, have occasionally noted strange anomalies. A signal from a spacecraft orbiting Mars or flying past Jupiter will arrive with a tiny, unexplained delay or carry a faint, ghostly echo of itself. Most of the time, the culprit is mundane, a glitch in the onboard computer, a burst of solar static, or an error in the ground station's own processing. These are quickly identified and filed away, but a handful of these events resist all standard explanations. They are subtle, transient, and they linger in the logs as unsolved puzzles. One fringe but captivating hypothesis looks not at the spacecraft nor at our own technology, but at the invisible sea we are sailing through. Our solar system is currently moving through a wispy, diffuse cloud of interstellar material known as the local interstellar cloud or the local fluff. This is a tenuous remnant of the much larger molecular clouds that fill our galactic arm. Within this local fluff, there could exist tiny, incredibly dense knots of cold gas and dust, miniature versions of the dark clumps we see in places like the Coalsack Nebula. These knots would be nearly impossible to detect directly. Now, imagine a radio signal from the Cassini probe at Saturn, traveling at the speed of light back to Earth. On its journey, it passes through this local fluff. If the signal's path grazes one of these hypothetical dense, cold clumps, something extraordinary could happen. According to Einstein's theory of general relativity, any mass warps the fabric of space-time. Even a small, dense knot of matter would create a tiny gravitational lens. This lens could bend the signal's path, causing a minute delay as the light takes a slightly longer route around the knot. It could even split the signal, creating multiple paths that arrive at our telescopes at slightly different times, producing that elusive echo. In essence, the local fluff could be acting as a natural, chaotic interferometer, distorting our communications with the faintest touch of gravity. It's a cosmic hall of mirrors made of frozen hydrogen and dust. While the odds of such precise alignment are low, the sheer volume of signals we send and receive across the solar system makes it statistically possible that we've brushed against this hidden structure. These anomalous echoes would be the signature of our solar system's intimate passage through the galaxy's leftover construction materials, a reminder that even the space between our planets is not perfectly empty. It is a subtle, whispering medium that can, on rare occasions, leave its fingerprint on our most precise conversations across the void. These ghostly echoes from our own backyard hint at a hidden architecture in nearby space, but the true scale of cosmic timing reveals itself in events that unfold over years, not milliseconds. Deep radio sky surveys have begun to catalogue a new, deeply strange class of object known as ultra-long-period radio transients. Unlike the frantic blips of fast radio bursts, these sources are patient. They switch on, becoming bright radio beacons for weeks, months, or even a full year. Then, with no warning, they disappear into the silence for a decade or more. Their periods are not measured in seconds, but in human lifetimes. What natural process has an on and off switch that takes years to flip? One compelling theory places them directly within the environment of a molecular cloud. Imagine a neutron star, the dense corpse of an exploded sun, on a long elliptical orbit through a vast cloud. For most of its decades-long journey, it travels through the near-perfect vacuum of interstellar space, silent and dark. But when its path finally plunges it into the dense outer layers of the cloud, everything changes. The cloud's gas and dust, sparse to us but thick compared to empty space, begins to swirl onto the neutron star's surface. As that material accretes, it heats to millions of degrees, igniting a torrent of radio emission that makes the star shine brightly in our telescopes. The transient is on for as long as the star is deep inside the cloud. Then it completes its orbit, exits the cloud's far side, and the fuel supply is cut off. The radio beacon shuts down, and the object vanishes from our view, not to return until its orbit brings it back into the cloud perhaps 50 years later. We could be witnessing the slow, rhythmic feeding of a cosmic predator as it periodically enters a galactic reservoir. The other possibility is even more extreme, a magnetar in a state of suspended animation. Magnetars are neutron stars with magnetic fields so powerful they can literally crack the star's crust, producing starquakes and brilliant X-ray flares. Perhaps an ultra-long period transient is a magnetar that enters a rare, decades-long quiet phase, its magnetic field temporarily frozen in a stable configuration. Then a slow buildup of internal stress finally reaches a breaking point, the field reconfigured, and a year-long eruption of radio waves is released as the star settles into a new equilibrium. These objects challenge our perception of cosmic time, forcing us to consider that some of the universe's most dramatic radio shows operate on a schedule we are only beginning to perceive. If ultra-long period transients are defined by their unexpected appearance, our next signal is defined by a profound and puzzling absence. It centers on one of the most famous dead stars in the sky, the Geminga pulsar. Located just about 800 light-years away in the constellation Gemini, Geminga is a powerhouse. It is one of the brightest sources of gamma rays in the entire sky, a furious beacon of the highest energy light, generated as the spinning neutron star's intense magnetic field whips particles to near light speed. We can see its powerful gamma ray pulse with clockwork precision. We can even detect a faint X-ray pulsation. But for decades, one thing was missing: the steady radio pulse that characterizes almost every other known pulsar. Geminga was radio silent. This was baffling. A pulsar's radio beam is like a lighthouse's rotating light, a byproduct of its spinning magnetic field. Geminga had the spin, it had the magnetic field, but where was the radio beam? Astronomers eventually detected an incredibly faint, whisper-thin radio pulse from Geminga, but it remains anomalously weak. The leading explanation for its historic silence points directly to its environment, a suspected but invisible supernova remnant or molecular cloud. When a massive star explodes to create a pulsar, it blasts its outer layers into space, creating an expanding bubble of hot gas and debris called a supernova remnant. This remnant should glow in radio waves for tens of thousands of years. Geminga is young enough that its remnant should still be visible, yet we see no clear radio shell around it. The hypothesis is that Geminga's expanding remnant, or a pre-existing molecular cloud it is plowing into, is not empty. It is filled with a dense ionized plasma. This hot, charged gas acts like a cosmic fog, absorbing the pulsar's radio beam before it can escape into interstellar space. The radio photons are essentially scattered and smothered at their source. Only the highest energy gamma rays, which punch through the fog unimpeded, reach us clearly. It is as if Geminga is shouting to us, but its voice is being muffled by a thick blanket it carries with it. This silent cloud neighbor presents a haunting possibility that the galaxy could be filled with similar radio-quiet pulsars, their brilliant gamma-ray hearts hidden within cocoons of their own making, detectable only by the silent, penetrating light that can escape their shrouds. We must then wonder how many other brilliant cosmic lighthouses are lost in the fog, their radio voices silenced by the very clouds that birthed them. The silent gamma-ray scream of Geminga shows us how clouds can hide a star's true voice, but sometimes the most common signal of all becomes the strangest. For astronomers, the 21-centimeter line is the most fundamental tool in the cosmic toolbox. It is the radio whisper of cold, neutral hydrogen, the basic ingredient of every star and galaxy. Whenever the single proton and electron in a hydrogen atom flip their mutual spin, they emit or absorb a photon with a wavelength of precisely 21 centimeters. Because hydrogen is everywhere, this line allows us to map the structure of our own galaxy and others, tracing the vast, swirling arms of interstellar gas. It is the universal background music of the cosmos, but in certain molecular clouds, this reliable signal begins to act strangely. When we point our radio telescopes at a bright background source, like a distant quasar, we expect the intervening cloud of hydrogen to absorb some of that light at the 21-centimeter frequency, creating a dip in the spectrum. The depth and shape of that dip tell us the cloud's density, temperature, and motion. Yet, in numerous clouds, the dip is all wrong. Sometimes it is far too deep, as if the cloud is impossibly cold and dense. Other times, it is suspiciously shallow or shows multiple jagged peaks instead of a smooth curve. These are the 21-centimeter line anomalies, and they imply that our basic understanding of these clouds is incomplete. One explanation lies in hidden structures. We tend to think of a molecular cloud as a somewhat uniform blob, but it could be more like a froth of ultra-dense filaments and sheets, structures so fine our telescopes blur them into a single signal. If the background quasar's light passes through a particularly dense knot in this cosmic foam, it would create an absorption dip much deeper than the cloud's average would predict. It is like judging the thickness of a forest by looking at one giant red wood you happen to line up with instead of the entire woodland. The anomalies could be a sign that these clouds are far more lumpy and textured on small scales than we ever imagined. Another possibility involves the invisible hand of magnetism. Turbulent magnetic fields threading the cloud can affect how the hydrogen atoms interact with passing radio waves. If the fields are highly ordered and powerful, they could theoretically polarize the 21-centimeter emission, altering the absorption profile in ways our standard models do not account for. we would be seeing not just the cloud's gas, but the ghostly imprint of its magnetic skeleton. Then there is the most profound and most speculative idea. What if these anomalies are not about the cloud at all, but about something passing through it? Some theorists have proposed that certain types of dark matter, the mysterious substance that makes up most of the universe's mass, could interact very weakly with normal hydrogen. If a cloud were permeated by a certain kind of dark matter particle, that interaction could subtly change the energy levels of the hydrogen atoms, shifting or distorting the 21-centimeter line we observe. In this scenario, the anomaly is not a puzzle about gas, but a potential clue to the universe's greatest missing piece. The humble 21-centimeter line, our trusted mapmaker, becomes a detective, hinting at invisible architecture within the clouds, forces we cannot see, and perhaps even the shadow of dark matter itself. A tool we thought we understood is now asking us questions we are only beginning to formulate. The heartbreaking truth about BLC-1 arrived not with a bang, but with the meticulous hum of forensic analysis. The initial euphoria of a signal from our closest stellar neighbor gave way to a rigorous process of elimination. Researchers at Breakthrough Listen and independent teams began dissecting the signal's properties, comparing it to a vast library of known radio frequency interference. The breakthrough clue was in the harmonics. The BLC-1 signal was not a pure, fundamental frequency. It displayed faint, ghostly echoes of itself at precise mathematical multiples of its main frequency. This is a classic fingerprint of human electronics, specifically a poorly shielded terrestrial oscillator, the kind found in countless clocks, computers, and consumer devices. The signal's drift, once so suggestive of a distant planet's motion, could be perfectly replicated by the Doppler shift caused by a satellite or aircraft moving relative to the telescope. The verdict became inescapable. We were not hearing Proxima Centauri. We were hearing ourselves, our own technological chatter reflected back at us in a moment of cosmic irony. This episode is a masterclass in the monumental challenge facing the search for extraterrestrial intelligence. Our planet is a cacophony. We are enveloped in a dense fog of radio noise, from cell phones and Wi-Fi to television broadcasts and radar pulses. Our most sensitive telescopes must listen through this perpetual storm, but the interference doesn't stop at our atmosphere. A genuine signal from deep space must then navigate the interstellar medium itself, the wispy plasma and molecular cloud filaments that fill our galaxy. This medium can act like a fun hall of mirrors, scattering and distorting a signal. A clean, artificial-looking transmission from a distant star could arrive at our telescope smeared, fragmented, and contaminated by the very clouds it passed through, making it look suspiciously like the messy, harmonic-laden interference we create right here. BLC-1 stands as a monument to our greatest obstacle, not the silence of the cosmos, but the incredible difficulty of hearing a single, true whisper within the endless roar of both Earth and the galaxy. It forces us to build better filters, to listen more cleverly, and to accept that the most exciting signal is often the one we must, with rigorous sadness, learn to dismiss. The BLC-1 disappointment was a lesson in cosmic noise, but it did not end the search, it refined it. If a civilization wanted to hide or simply existed on a scale we could not yet perceive, where would we look? The answer may lie not in the signals they send, but in the mess they leave behind. This is the frontier of technosignature hunting, and it is leading scientists directly into the chemical hearts of interstellar molecular clouds. Instead of listening for a deliberate hello, they are now learning to sniff the air of the cosmos for industrial exhaust. Think of it as cosmic forensics. When we look at the spectrum of a cloud, we see the fingerprint of every molecule within it, a barcode of creation. Chemical reactions in space tend toward a certain natural equilibrium, governed by temperature, pressure, and the raw elements available. But what if you found a cloud where that balance was completely off? Imagine detecting a cloud with a bizarre overabundance of a specific, complex organic molecule, like a particular amino acid or a component of DNA. In nature, such molecules are usually present in trace amounts among many others. A glaring excess of one could suggest something is manufacturing it, concentrating what would normally be a diffuse ingredient. Even more telling would be an anomaly in isotopic ratios. Isotopes are different forms of the same element, like carbon-12 and the slightly heavier carbon-13. Natural processes treat them almost identically, so they appear in a predictable ratio. If you found a pocket of gas where that ratio was wildly skewed, heavily favoring one isotope over another, it would be a screaming red flag. On Earth, we create such imbalances all the time, in nuclear reactors or through advanced industrial separation processes. It is a signature of technology that manipulates matter at its most fundamental level. A cloud exhibiting this would not be broadcasting a message, it would be leaking evidence of its own artificial alteration. The most subtle technosignature of all might be waste heat. Every energy-intensive process, from powering cities to running supercomputers, produces heat as a byproduct. For a civilization hidden within a dense molecular cloud, that waste heat would need to be dissipated. While it might be masked by the warmth of young stars, an extremely advanced society could theoretically produce a detectable infrared or microwave glow that doesn't match any known stellar or chemical model, a thermal footprint of immense activity shrouded by dust. This shifts the search from interception to investigation. We are no longer just radio listeners, we are cosmic detectives scanning the chemical ledgers of nebulae for entries that do not balance, for elements in the wrong proportions, for the gentle warmth of a hidden machine. The greatest discovery may not be a signal aimed at us, but the silent, lingering trace of someone else's home, a fingerprint on the window of a stellar nursery. Chemical forensics and waste heat are silent clues, but the next leap in solving these 25 mysteries will come from an instrument with an eye 10 billion times more sensitive than our own. In late 2025, the Vera Rubin Observatory will begin its decade-long legacy survey of space and time, scanning the entire southern sky every 3 nights with a camera the size of a small car. This is not just another telescope, it is a time machine for the visible universe. Where radio telescopes hear the crackles and hums, the LSST will watch tirelessly for anything that changes, blinks, or moves. Its power lies in correlation, the ability to see 2 different stories of the same event unfold simultaneously. Imagine a brilliant fast radio burst streaks through our detectors. For years, its origin has been a frustrating radio-only puzzle. But with the LSST data, we could rewind. We could look at that exact patch of sky, at the precise millisecond the burst arrived, and search for an optical counterpart. Did a star in that distant galaxy flare with unprecedented violence at the same instant? Did a magnetar in a foreground molecular cloud light up invisible light? By marrying the radio scream to an optical fingerprint, we could finally identify the engine behind these colossal explosions. The reverse is equally thrilling. The LSST will discover millions of new optical transients, stars that flare, fade, or erupt in ways we have never seen. For each one, we can then ask a critical question. Did that optical event produce a radio echo? By cross-referencing these new LSST discoveries with radio archives from telescopes like CHIME or the Future Square Kilometre Array, we will find a new class of object, the silent optical transient. These would be stars that undergo dramatic visible changes without the expected radio chatter, perhaps because they are shrouded in a dense cocoon of molecular cloud material that smothers their radio voice just like Geminga. Each silent event would be a new enigma, pointing to a hidden environment or a new type of physics that only reveals itself in one spectrum of light. The Vera Rubin Observatory will turn the sky into a living documentary, frame by frame, for 10 years. In that vast movie, the unexplained signals from interstellar clouds will finally have a visible co-star, allowing us to match the invisible radio whisper with a face we can see, or discover a brilliant actor performing in utter silence, a discovery that would rewrite the script of stellar life and death. The Vera Rubin Observatory will give us the eyes to see the actors, but we will need a new ear to finally hear their lines. That ear is being built right now across 2 continents, and it promises to listen to the universe with a sensitivity beyond anything we have ever known. The Square Kilometer Array, or SCAR, is not a single dish but a symphony of them. Thousands of individual radio antennas will be spread across the remote deserts of South Africa and the outback of Western Australia, all networked together to act as one colossal instrument. Its name is literal. Its total collecting area will eventually span over 1 square kilometer. This gives it an almost inconceivable power, the ability to detect a signal as faint as an airport radar on a planet orbiting a star tens of light years away. For the dark, whispering clouds, this changes everything. Where current telescopes hear only the loudest cracks and booms from these nebulae, the SKA will tune into the murmur. It will map the radio sky not in years but in days, creating a real-time, dynamic movie of the cosmos radio emissions. This speed and sensitivity mean it will catch signals that are currently invisible to us, fleeting whispers from within molecular clouds that last only seconds or milliseconds. We could discover an entire zoo of new, ultra-faint radio transients, phenomena so subtle they have been hiding in the static just below our detection threshold. Perhaps these will be the gentle radio sighs of brown dwarfs being born, or the faint, coherent pulses from protoplanetary disks as planets coalesce. The SKA could resolve the long-standing mystery of fast radio bursts not just by finding more of them, but by detecting their incredibly faint afterglows or pinpointing their home galaxies with unprecedented precision, finally telling us if they are born in the chaos of stellar nurseries or the depths of intergalactic space. Most tantalizing of all is its potential to hear structure in the noise. Right now, a signal must be relatively strong and simple for us to distinguish it from background static. The SKA's phenomenal sensitivity could allow it to detect incredibly weak signals that nonetheless carry complex patterns, subtle modulations or repeating sequences too faint for any other instrument to resolve. It will be like moving from hearing only shouts in a crowded stadium to being able to discern every individual conversation. If there are any deliberate, structured signals hiding within the radio emissions of molecular clouds, be they natural cosmic lasers with bizarre precision or something else entirely, the SKA is the instrument that could finally tease them out from the cosmic hum. This telescope won't just find answers, it will redefine the questions. We may discover that what we thought was random noise is actually a rich, low language of the clouds, a language we are only now building the dictionary to understand. The silence we perceive may simply be a limit of our own hearing, and the SKA is about to give the universe a new voice. The universe is ancient and unimaginably vast, filled with hundreds of billions of galaxies, each with hundreds of billions of stars. The numbers alone suggest life should be common, even intelligence. Yet when we listen, we hear only a cosmic static punctuated by natural mysteries. This profound silence is the heart of the Fermi paradox, a simple, haunting question posed by physicist Enrico Fermi. If they are out there, where is everybody? Where are the city lights of galactic empires, the clear radio broadcasts, the unmistakable signs of cosmic engineering? One speculative answer to this great silence brings us back to the very clouds we have been exploring. It is called the cloud sanctuary hypothesis. Imagine a civilization that has survived its technological adolescence, one that has looked out into a galaxy potentially filled with other, younger, and possibly aggressive intelligences. Their primary goal may no longer be expansion or broadcasting, but survival and stability. Where would such a civilization hide? The answer could be in the last place. A young, curious species like ours would think to look for advanced life inside the dark, cold, and chaotic interstellar molecular clouds. To us, these are nurseries and tombs. To them, they could be the perfect fortress. A dense molecular cloud offers profound protection. Its thick veils of gas and dust are a natural radiation shield, blocking harmful cosmic rays and gamma rays from nearby supernova. It obscures visible light, rendering any structures within virtually invisible to optical telescopes. Even our most powerful infrared eyes, which can pierce some dust, would struggle to distinguish the waste heat of a civilization from the natural warmth of young stars and protostars also forming inside. But the sanctuary idea goes beyond mere hiding. A truly advanced society might not just live in a cloud, they might harness it. The cloud itself becomes their resource, a vast reservoir of hydrogen, helium, and complex organic molecules, the raw materials for energy and life. They could build their habitats on dark, rocky bodies deep within the fog, or construct vast, diffuse structures that float among the dust grains, all cloaked by the nebula's natural emissions. Their communications would be a key part of the strategy. Instead of powerful, omnidirectional broadcasts that shout their location to the galaxy, they might use incredibly focused, laser-like transmissions, point-to-point links that are virtually undetectable unless you are in the precise line of sight. Or they might use a physics we have not yet discovered, communicating through quantum entanglement or modulated neutrinos, methods that leave no trace on the conventional radio spectrum we monitor. Most intriguingly, they might deliberately camouflage their signals to look like natural phenomena, that strange, repeating pulse from a Taurus cloud. Not a protostar's birth cry, but a shielded power reactor's cycling signature, that anomalous spectral line in Ophiuchus, not an unknown molecule, but a faint, engineered beacon for other sanctuary dwellers, broadcast on a frequency that mimics chemistry. The unexplained circular polarization from DR21, a side effect of their propulsion or energy systems leaking into the cloud's ambient noise. In this scenario, our entire catalog of 25 unexplained signals could be something far more profound than cosmic weather. They could be the faint, scattered echoes of a galactic community that has chosen silence, a civilization that has moved past the need to be found and into the art of remaining hidden. They are not missing from the universe, they are all around us, watching from within the shadows of creation itself, their presence woven into the static we have labeled as natural. The great silence of the Fermi paradox may not be silence at all. It may be a conversation happening just next door, in a language of whispers and dust, waiting for us to finally understand the grammar of the clouds. The cloud sanctuary hypothesis paints a picture of deliberate silence, but there is another, more fundamental kind of silence woven into the fabric of reality. At the most microscopic level, the universe is never truly quiet. Even in a perfect vacuum at absolute zero, there is a seething, irreducible hum. This is quantum noise, the fundamental jitter of existence imposed by Heisenberg's uncertainty principle. It tells us there is a limit, a hard boundary to how precisely we can measure anything. We can never know both the exact position and momentum of a particle. The very act of observation disturbs the system. For radio astronomy, this translates into a profound and inescapable truth. There is a minimum noise floor for every instrument, a hiss born not from our technology's imperfections, but from the quantum nature of light and matter itself. As our telescopes grow more sensitive, pushing toward the theoretical limits of detection, we approach this ultimate background static of the cosmos. Now consider the faintest whispers from interstellar clouds, the signals so weak they are barely a flicker above the noise. Could some of the anomalies we chase, the fleeting blips we dismiss as instrumental error, actually be real astrophysical events whose strength is exactly at this quantum limit? Their truth would be forever entangled with the background fuzz of reality, making them fundamentally unverifiable by any measurement. They would be ghosts in the quantum machine. This leads to an even more profound speculation. The extreme environments within molecular clouds, where magnetic fields are twisted to breaking point and gravity battles turbulent plasma, could be natural laboratories for physics we have never seen. Some theorists suggest these conditions might allow for the faintest manifestation of quantum gravity effects, the elusive union of Einstein's relativity with quantum mechanics. If such effects produce radio emissions, they would be unimaginably weak, likely buried deep within that universal quantum noise. The signal would be there, a whisper from the universe's deepest operating system, but we could never isolate it with certainty. It would be the ultimate unexplained signal, not because it is mysterious, but because it lives at the very edge of what is scientifically knowable. Our pursuit of these cosmic whispers, then, becomes a philosophical journey as much as a scientific one. We are not just building better telescopes, we are confronting the fundamental architecture of knowledge. The clouds may hold answers that the universe, by its very quantum nature, is structured to keep just out of reach. The final mystery may not be in the signal, but in the silence that inevitably surrounds it. From the startling red pen circle of the wow signal to the faint quantum whispers at the edge of reality, this journey has revealed a cosmos far noisier and more mysterious than we ever imagined. We have traversed a landscape of rhythmic heartbeats from the galactic core, witnessed the explosive tantrums of infant stars in distant clouds, and learned to see the dark voids of space as potential sanctuaries, not emptiness. Each of these 25 unexplained signals, from the patient decade-long transients to the chemical anomalies in Ophiuchus, is more than a curiosity. It is a beacon, a brilliant flare marking the outer limits of our current understanding. These interstellar molecular clouds, those vast and frozen nurseries, are not passive backdrops. They are active, chaotic participants, cosmic laboratories where physics is stress-tested to its breaking point, and where the raw materials for life are stirred into impossible complexity. They are also the universe's ultimate shrouds, capable of hiding black holes, muffling pulsars, and perhaps even concealing answers to our oldest questions. Every anomalous blip on our charts, every spectral line that does not fit, is a gift. It is the universe politely pointing out where our maps are blank, where our equations fall short, where a deeper truth lies waiting. This relentless, humbling ignorance is not a failure, it is the very engine of science. It is what drove Jansky to build his merry-go-round, what compels us to construct the square-kilometer array, and what will send even grander observatories into the void in decades to come. The search is never truly for a final answer, but for a better question. So keep looking up, follow the data as it streams in from Chile and from the deserts where the SKA will soon listen. The greatest story ever told is still being written, in the silent spaces between the stars and in the static between the stations. The next chapter, the one that changes everything, could be arriving at this very moment, a ripple traveling at the speed of light, already piercing the dark heart of a cloud, already on its way to us. All we have to do is keep listening.